Welcome back to this module review of caches. In this lesson I will describe different cache metrics and discuss how the hit time of a cache can be improved. In this lesson I will discuss some basic cache optimization techniques. But first we need to define some cache performance metrics. What do we want to improve? The first cache performance metric is the hit rate. The hit rate is given by the number of cache hits divided by the number of cache accesses. Similarly, the miss rate is defined as the number of cache misses divided by the number of cache accesses, which by definition equals 1 minus the hit rate. Unfortunately, both these cache metrics do not factor in the cost for a hit and the cost of a miss. Therefore, the hit time will be used to define the time for a hit, and the miss penalty will define the extra cost of a miss. This gives us a very important equation called the average memory access time, or AMAT. The AMAT is given by the hit time plus the miss rate times the miss penalty. That's the goal. That's what we want to optimize in this lesson. To understand what causes cache misses, where cache misses come from, we categorize them into 3 different types of cache misses. For this we use a famous model called the 3 C's, because every cache miss is classified as a cache miss that starts with the letter C. The first one are compulsory misses, also called cold start misses. These are misses that are caused by the fact that the first access, because we fetch data on demand, the first access to a block is always a miss. We can measure in a simulator, we can measure the compulsory misses by counting the number of misses in a hypothetical cache of infinite size. The second type of cache misses are capacity misses. Because the cache cannot contain all blocks that are needed now and in the near future, capacity misses will occur because blocks will be discarded and later brought to the cache again, later retrieved. You can measure those in a simulator by counting the number of misses in a fully associative cache with optimal replacement. Then there are conflict misses. These are misses that occur because several blocks map to the same cache block that map to the same set. They're also called collision misses because the cache blocks collide on the same set. And basically all other misses can be classified as conflict misses. Let's get back to our original question: how do we improve the average memory access time? Right? I talked about larger block size, I talked about higher associativity, which are both aimed at reducing the miss rate. I will very briefly now talk about reducing the hit time by using small and simple caches, and techniques to reduce the miss penalty by using multi-level caches and by giving priority to read misses over writes. First, small and simple caches. Why should we use small and simple caches? This figure here shows the access time of a cache for different associativity and for different cache sizes. Here at the bottom we have different cache sizes going from 16 kilobyte to 30 kilobyte up to 256 kilobyte. And on the vertical axis we show the access time in picoseconds, right? These results have been obtained using a cache simulator called Cacti. We see in general that increasing the cache size increases the cache access time. Not always, but in most cases. We also see that increasing the associativity also increases the cache access time. So as a rule of thumb we can say larger caches have larger hit time, and higher associativity also has higher hit time. Here's another technique that I would classify as a a simple cache optimization technique. The use of a split cache. In one cycle of our canonical pipeline, 5-state pipeline, we need to fetch an instruction in the instruction fetch state, and we need to read the data from cache for a load or store data to a cache, store. If we have only one cache that is unified, the cache must have 2 read ports and 1 write port. Unfortunately, multi-ported caches are complexer and therefore slower, larger, and more power consuming than a single-ported cache. For that reason, it's better to use a split cache. That means we have one cache for instructions, typically called the instruction cache, and one cache for data, Dcache or $. Now, in one cycle, look here, we can fetch an instruction and we can access the data both using a single ported cache. This completes this lesson. Thanks for watching. In the next lesson, I will discuss some basic optimizations that improve the cache miss rate. Hope to see you back.